In this video, we'll start the discussion of chapter 2, and basically we'll discuss part of section 2.1. So in this part, we'll try to start from a equation, right? Start from assuming a equation not we cannot solve, right? We want to get some qualitative information from the differential equation, right? So let's see that now we assume we have a differential equation, first order differential equation, right? This is the whole chapter 2 is about first order differential equation, right? And first section is discussing whenever you have a function you cannot solve, how do you get some qualitative information, right? How do you get some possibly decide the function and the function, the solution is increasing or decreasing or concave up or concave down at local maximum, local minimum, right? We want to get some information like that. Okay, let's see that. So let's start from a function we cannot solve, right? So let's assume we have a function dy over dt dx. Let's use x as our variable. Normally we use x or t. In this case, we use x. So y is a function of x. Y might be a function, y might be the temperature or population or other things we are interested, right? I suppose, right? Suppose we cannot find a solution for this function, right? You suppose we don't know how to solve it, right? And also we don't know how to solve it analytically, right? We cannot get y equal to 5x such that 5x is a solution for this equation. Now we still want to get some idea how does the function change, right? How does the solution of this function change? So we try to understand. So our goal here is try to extract important information from the differential equation, right? Information. How do we do that, right? You have dx over dt. Now, clearly you can see that if you have f of xy is positive, the function will be increasing, right? So get our slope function. If you have a first order differential equation, you get a slope function. You get, this is basically a slope function. Slope function, right? So we have two cases. First one here is if f of x, y is positive, then y here is increasing, right? And if f of x, y is less than 0, y is decreasing. Now from calculus 1, we know this must be true, right? So we can solve for the inequality f of x, y being positive or negative. You get some information of when the solution is increasing and when the solution is negative, right? And also, using the slope function, you can try to sketch the change of the function over at any point, right? For any xy, you can solve for dy over dx. You get some kind of slope at each point, right? So imagine you want to understand what does the solution look like over a rectangle, right? Then you can let's see that, right? Then you can evaluate, sorry, evaluate f of x, y uh, over a rectangle area, rectangular grid, fix some point in the rectangular domain, right? And and uh, draw a, a line element at each x, y with slope f of x, y, right? That line is indicating if your function actually past that point, where the function should go, right? Go up or down or go flat, right? So it's basically this kind of uh, line segments, line elements on the rectangular grid give you a vector field, right? So we'll see example directional field. So then uh, we get the direction field of what of dy over dx equal to f of xy, right? So let's see an easy example, right? So for sure, if you want to understand better about this solution of the differential equation, you need to make your grid finer and finer, right? You should control the accuracy, right? The error. And so, but in general, we will have a good understanding of what does the solution look like if your grid is fine enough, right? Let's see example. Our example is given by dy over dx is 0.2 xy, right? Let's make a grid over the interval, the region from, let's make an easy grid, right, for our calculation. And for sure, we can do that using a computer now. But let's try to understand the idea, right? So let's try to make our grid and make it to be 0, 1, 2, 3, 0, 1, 2, 3. So you have what? 4 times 16 points, right? You can do all the calculations on the grid, right? For example, if you have x is 0, y is 0, and so when x or y equal to 0, then dy over dx is 0, which means you have a flat, right? Let's use green to for our vector field line segment. So always flat because derivative is 0, right? And if you have, let's try to do the other, x, y equal to 1, the slope is 0.2, right? 0. Okay, so when x, y equal to 1, then dy over dx is 0.2. So you can try to sketch a line segment with a slope 0.2, right? And you can do all the others if you want. This one is getting steeper, and this one is also getting a bit steeper. This is too much, so a bit steeper and a bit steeper here, right? If you have this will be same as that. So this will be same as that. And after that, you get even steeper here, range. And this is a bit whatever in between range. You can put an arrow above it to make sure this is how does our solution go in this direction. So you have some understanding what does the how does the graph change as x getting bigger and bigger, right? So let me try to bring in a picture here. So using computer, you can do that, which is this direction field of the same differential equation. Let me put it here. Right. So this is basically uh, what does above the top half, you have direct direction field of this example here, right? And later we can solve it, and our solution will be uh, y equal to c times e to 0.1 x squared. You can try to see that if c positive, c equal to 0, or c less than 0, to get a uh, different different solutions based on your initial conditions or other conditions, right? But all the green, red, and blue are all the solution of this differential equation, right? So this is basically in this video we discussed whenever you have a first order differential equation, you get a slope function. You have a slope function, you get a direction field. You have a direction field, and you can approximate. No, you can get some important information, qualitative information from the differential equation, right? Increasing, decreasing, something like that. And right. Okay.